Hello, everybody. Hi. Oh, man. Let me clean up my desktop a little bit in preparation for this. Hi. How's everything? How's everyone doing? How is everything? Welcome to another Ask an Astronomer. I know I did one on Monday, and it's weird. You're probably wondering why you're doing a second one this week. Well, this is my regular. I'm going to do a monthly thing where I introduce stargazing. I just thought, let's just put out a whole bunch of dumb content. But I appreciate you watching wherever you are or whenever you're watching this. I'm doing well. It's raining, which is really welcome considering it's been very sunny and hot here, and so I'm pretty happy that it's raining. Today, the last time we talked about systematic racism, and I think I was really proud of that. And today I want to talk a little bit about some more astronomy stuff, kind of like what we've been talking about with using Space Engine. And I want to talk about galaxies. So there's going to be a difference in what we've talked about last time on this to now. But as always, if you're watching and you have questions at any point, just write them in the chat. I've got the chat right here, and I'll take a look at that. But this week, I want to spend an hour talking about galaxies. And this is exciting for me because I'm a galaxy astronomer. In previous talks, I've talked about things that, while I understand a little bit about them, and I have some history of discussing them, I wasn't as knowledgeable as I am about galaxies, and specifically distant galaxies. But we're going to start by talking about just the kind of different types of galaxies and what's going on in a galaxy. The last astronomy discussion, we talked about the Milky Way, which I'm showing here. So if I bring Space Engine back up, you can see the Milky Way right here. And so hopefully you remember a little bit about the Milky Way here. And we'll start by talking about the Milky Way, but we'll also talk about other types of galaxies like these little Magellanic Clouds. This is a large and small Magellanic Cloud. So we talk a little bit about, I think at the end, about some of the other galaxies in our galaxy neighborhood in the local group of galaxies. But we're going to talk about a lot of galaxies. And so I want you to point out right now that Space Engine is actually simulating other galaxies. They're the other little dots around here. There's no stars in this image. Every dot is representing a galaxy. Like if I were to click on this, you'd see that it was, oh wait, I have to turn on this. It's Galaxies NGC 7095, right? Or if I click on this one, it's RG, which is a randomly generated galaxy, NGC 2915. But these are actual galaxies, right? And so Space Engine is trying to simulate that. But so when you look out at night in the night sky, you're actually seeing stars, and unless you have really good vision or you live in the southern hemisphere, you're not seeing any galaxies. And when we fly outside of the galaxy, remember all the stars are in here. So to start, let's define what a galaxy is. And I defined it last time we talked about the Milky Way, but I want to define what a galaxy is. A galaxy is just a collection of stars that are held together by gravity. And so this right here, this flat disk of the Milky Way, is a collection of about 100 billion to 400 billion-ish stars, okay? Gravity holds them together. The reason that they're a flat disk, as we discussed last time, is because of how it was formed. Whereas the gas was collapsing to form this galaxy, it spread out into a flat plane, and gravity pulled it into that plane and constructed that plane, and it spread out in the same way that anything when you spin it will start to flatten and spin out kind of like a pizza dough. It's a little more complicated than that, but for right now, that's a good explanation. And so you can see it's very thin, right, versus how big it is. And we're located somewhere, like if I center on the sun, you can see that the sun in the center here is not centered in the middle there. The sun's located way over here in one of the arms, right? So if we were to go zoom in, the sun is over here versus not being in the center. Okay, so this is what we call a spiral galaxy. We'll talk about the types of galaxies in a second. But essentially, galaxies are much larger than stars because they're an accumulation of stars. And so you can kind of think of this like if stars are people, this would be a country, I guess, right? And the country is composed of many states and cities, and similarly, like a galaxy is composed of different spiral arms and different clusters of stars. It'd be like a country that had 100 billion people in it. The other thing is that galaxies are mostly empty space. They're mostly just completely empty, right? Like if we zoom in, and it's hard because I'm zooming very fast, you could start to see the stars, but the distances between these stars is not like, it's not like you're here and you're just like a hop, skip, and a jump, right? Like the distance between the sun and our nearest star neighbor is an enormous distance, right? It's multiple parsecs, right? So multiple light years. And so that light taking, years, right? The farthest thing humans have sent, I think today I saw is like 17 light days? Like distance to Voyager in light days. Light days or light hours? Light hours. Yeah, it's about 19.6 light hours. So almost 20 light hours, right? So that means it takes light 20 hours to get from that telescope in space to us. That's the farthest thing we've sent from the Earth, right? And now, remember, the nearest stars are light years away, right? So enormous amounts of empty distance between space. And so that means that, like, you know, it looks like these are larger, but, you know, if we center this one random star here and zoom in, I gotta really slow down so we can get closer and closer and closer to it. Whoop. I'm going way too fast. But like, as we get closer and closer to it, you see that it's not like as large as it looks. Whoops. I gotta put on my glasses here. That's 2 stars. But these stars, each individual one, whoop, whoa. If we go there, and again, still taking a while to get there, you see that it just looks large because it's incredibly bright, but it's not actually that large in comparison to the size of the galaxy. So most of what a galaxy is just empty space between stars, right? And so if you take 2 galaxies and you crash those 2 galaxies into each other, you just crash. See, look at how long it took just to get to this star, right? And so here's this one star, and you can see the Milky Way surrounding it, right? And then the other star there. The other star looks big, but it's actually very, very far away from that other star. And these are just some random stars, right? Like if I zoom out, it looks larger, but it's because I'm really zooming pretty fast, right? So keep zooming. And now you can start to see as we're zooming out farther and faster that the other stars are coming. And then we zoom out far enough and we see that we've got the Milky Way, right? So if I brighten this up a little bit so we can really see the Milky Way, you can see that if I were to take this galaxy and crash it into another galaxy, just crash them into each other, stars would just pass right by each other because there's so much empty space. And the way that we, I've said this on the stream before, but if you took our sun and shrunk it down to the size of like a grapefruit that I'm holding here in my hand, the nearest star in this shrunk down universe where I'm holding a sun is in Peru, which is quite a ways away, right? And so like, if you were one lonely grapefruit here in America and like you were rolling around, it'd be very difficult for you to go and randomly roll into one other grapefruit in Peru, right? That's quite a ways away. And so that's the thing, is that galaxies are mostly just empty space filled with quite a few stars. What really holds them together is not just the mass of the stuff in the stars, that makes up the stars and the gas and dust, but a bunch of material called dark matter, which we don't exactly know what it is, but it's most of the mass of the galaxy. It's like a big blob of dark matter. If I zoom out, you could imagine a big blob of dark matter that's in space. And the galaxy is just the bright light of the stars that have fallen into this dark matter ball. Okay? And so everything that you see, again, right around here, including this like big cluster in the background, these are all galaxies. Mostly are simulated galaxies by Space Engine, but they've also added in a bunch of real galaxies. Okay? And so when astronomers were first understanding galaxies in the 20s, I talked about this last time, they were confused by how far away they were, because they thought at the time that the Milky Way must be the entire universe. Because if the galaxies they were starting to measure their distances to, if they were actually that far away, then that would indicate that they were farther than anything they could ever thought were possible. And now we know that not only were they farther than that, but there are galaxies that are even farther that would have made an astronomer from the 20s destroy their brain in terms of the distances, because the galaxies that you're seeing here are more often than not just nearby galaxy neighbors, right? And there are galaxies that stretch out to the beginning of time. And so a galaxy, if it's a collection of stars, is a very complicated thing. I think stars are complicated. I'm not trying to lie about that. But stars live a life that has been pretty well prescribed. And stellar astronomers, if they're watching, are probably like confused by why I would even deign to say that, because stars are very complicated. But like a collection of stars has possibilities for interesting, weird physics and astronomy. And so when you have a galaxy's life is a very complicated thing, right? So you could imagine wondering, well, how did this galaxy form? How did it get its stars? Did it make more stars? Is it making stars now? Are there, what's the different colors about? Why is it a spiral, not, like some blob? And these are the questions of what's called galaxy evolution, which is a major topic in astronomy studies. But before we get into galaxy evolution, I want to talk about the history of us understanding galaxies. Maybe the earliest, most famous galaxy astronomer was a guy named Edwin Hubble, who we've named a space telescope after. And Edwin Hubble, he looked using a telescope that's north of Los Angeles at a bunch of galaxies, especially nearby galaxies. And he kind of came up with what we now call the Hubble tuning fork, which is kind of more a novelty in galaxy studies than anything. But I'm going to show you the Hubble tuning fork. I'm going to show you it in a kind of silly way here by just showing you it in Google. So here's a web page that I've got that shows this tuning fork. And if I take this and shrink it down, we can actually make it a little bit easier. We can really take a look at this because I want to showcase this. But Edwin Hubble had this classification scheme that was like, all right, I'm just going to take various types of galaxies that I see, and I'm just going to like try and understand what we've got. And so Hubble found essentially that he could see mostly like two types of galaxies when he was looking through a telescope. And some of them were ones like our own galaxy, right? So if I come over here, we can put our own galaxy on the right over my head, right? Milky Way. And those are galaxies he called spiral galaxies for obvious reasons. But then he also saw galaxies that were not spirals, that were like big, they didn't have any spiral arms. They kind of seemed like a big blob of stars. He called those elliptical galaxies. And in the spiral galaxies, he found that there were kind of two types, barred spirals and not barred spirals. So what does that mean? So if you look in the little picture, the little, the yellow here, and the red right up here, you can see that this yellow object has a bar across it, right? There's essentially the arms don't come and touch the center. They touch like some sort of structure that stretches across the center. So you can see in all three of these, there's some sort of structure of stars, and we have a bar in our galaxy as well. That's this right here. It's kind of hard to see, but the spiral arms don't go in all the way spiral into the center. They come to the edges of this bar here. And so those are called barred spiral galaxies. And so he said, all right, well, we've got barred spiral galaxies, we've got non-barred spiral galaxies. And he made this diagram, which is completely random in that he just said, well, let's take elliptical galaxies and say that elliptical galaxies, when I look at them, they're either kind of blobby or they're more spread out like a grain of rice. And we'll give them numbers between E0, kind of a perfectly round ball, to E7, E8, which are more and more spread out, more elliptical. And then let's have a spiral and say, depending on how loose and open the spiral arms are versus how intertwined and tight the spiral arms are, we'll say it's between an SA to an SC, right? So you can see that SAs have very tightly wound spirals, and then SCs are a little more open, ended. And the thing is our galaxy, if I click on it here, is an SBC, right? So SBC on this diagram means that it's a barred spiral with not super tightly wound spiral arms, right? Pretty classic. Right? If we go back to this and I look up like a SBA galaxy, we can look at something like this barred spiral galaxy here, which I don't know if you can see it very well in this diagram. Let's undo my crazy shrinking of this, and let's. There we go. And so you can see here that, if I shrink this again, that this galaxy here has a pretty tightly wound spiral with this pretty obvious bar that's in the center. Pretty cool, right? I don't know if my mouse, maybe this is the mouse. Yeah, I should be using the smaller mouse instead of the larger mouse. It's complicated. But, you can see that, like, in this, there are, actual examples of galaxies right here, like this SBA, which has a bar and it's pretty tightly wound, and the SBC, like our own galaxy, right? The Milky Way is maybe like this galaxy here, M83, right? Here are elliptical galaxies that he was seeing. No spiral arms, right? No spiral arms. And you can see E0 through E5 here, pretty blobby, like a big sphere, all the way to this very, spread out one. And he's thought that elliptical galaxies that were more spread out are likely very similar, maybe even progenitors, that a galaxy went through these steps before becoming a spiral galaxy. So that the tuning fork was like and an S0 galaxy, by the way, is a lenticular galaxy, which is like, it looks like a transition between the two. Like if you were to trace this all the way to becoming more like a spiral galaxy, becoming more elliptical, you might imagine going through a process like this to make a lenticular galaxy. And the thing is he thought at the time, oh, this is how this is how it is. It's that there's this evolution of galaxies from elliptical to spiral. And now we know that that's not the case at all. In fact, if anything, it's the other way around, which we'll talk about in a second. There's another type of galaxy that it was probably not as easy for him to describe, and he probably set these all out separately, if anything, that were called irregular galaxies. And here's a couple of classic irregular galaxies, like the large and small Magellanic Clouds. Like, if we go back to Space Engine and I turn off the window here, you can see the large and small Magellanic Clouds. They're over here. Whoop. Let's actually find them. They're over here. Whoops. And you can see that they're not exactly, although they've been drawn here, they're kind of weird blobs of stars. They've been put in Space Engine as these flat disks, but they are not flat disks. They're like some sort of crazy train wreck of stars. And it's probably because they don't have a huge amount of mass that has allowed them to collapse. And then on top of that, they've been ripped apart through interactions with galaxies. And then, there's peculiar galaxies here, which are generally classified by this guy ARP and some other people who looked and found all these peculiar galaxies. And these are galaxies that are in the process of being ripped apart because they're crashing into each other, which we'll talk in a second. So here's the tuning fork again, where Hubble thought, this is the way that galaxies go, right? And put irregulars on the side. But it's not how it is. But essentially, this sets up, I'm trying to show you a diagram that you're not actually seeing right there. See, and then the peculiar galaxies are up here. I was talking about, excuse me. The peculiar galaxy is where you see that they're probably a train wreck of stars. But this diagram, this tuning fork, is like a novelty, but it's not really how it actually goes. It's just mostly it was a classification novelty. So what's been interesting since the 20s and 30s and 40s is that astronomy has really gotten good at getting large populations of galaxies and putting these into catalogs. And so there's many catalogs of galaxies. The most famous is the NGC catalog. So if I Google NGC catalog, you can see that that's the new general catalog. It's not just galaxies, it's many deep sky objects. It was cataloged in 1888, but this, along with the Messier catalog and many others, have been used to classify galaxies. And on top of that, we have much more modern versions of these. But it's pretty amazing that these modern objects have been then easily studied to the point where many of the large galaxies, if you were to click on some NGC object, like if you NGC some galaxy, we could because there's a set of stars here, but if we go NGC 6, let's see if I can find one of my favorite 6774. No, that's not, it's NGC galaxies. My brain is breaking exactly which galaxies. NGC 1097. This is a classic one right there. 379. NGC 3079, right? And so these galaxies, they're the focus of a huge amount of study. This is a Hubble Space Telescope image because the most of the NGC galaxies are really, really close by. They're really well studied, especially by Hubble, and in the future they'll be studied by James Webb as well, because you can get a really good understanding of what's going on in the galaxy. So when you look at a picture of a galaxy, because it's gas and stars, you're seeing quite a bit of really interesting structure and things going on, right? So this is a Hubble image, and what they're doing is, I think, highlighting a lot of the star formation that's going on throughout this in the spiral arms. And this is a galaxy that's not actually shaped like a long wedge, but it's probably a spiral galaxy that's seen from the edge on. And so you could imagine that if I zoom back out here, I could get a very similar view of, and let's turn off the window here. I could get a very similar view, right, of this galaxy seen edge on. We can turn the thing right here, and now you can see that this would be a very similar type of thing where we'd be seeing this object edge on, as you do with this galaxy. And so you can see in the Hubble, you can see right there this really cool lumpy bubble of hot gas that's being pushed out from the center of the disk, right? So it's really amazing how having these nearby galaxies allows us to really understand what's going on, the processes going on that shape the way the galaxies exist, right? You can see also the Sombrero Galaxy. M104. I wonder if M104 or 4994. Let's look at if NGC 4594. I want to see if this object's in Space Engine. Space Engine. I'm not looking at these galaxies in Space Engine for an obvious reason. So NGC 4594, and that's because many of them are not as represented. Here's the Sombrero Galaxy in Space Engine, and it's fine. You know, it does an okay job, but it doesn't have the same, you know, structure. Like it's some representation that's not nearly as good as what you see in the actual galaxy. So if I pop back, you can see that you know, it's got the dust. It's got the dust ring around it, so it's doing a pretty admirable job, right? Like I'm not gonna lie, that's not so bad, right? If I bounce between the two, the simulation's not so bad, but many of the objects are not nearly this good. But what's incredible and why I started studying galaxies is that you can look at a picture of a galaxy and understand a galaxy, and like there's so much to unpack, right? When you look at a galaxy, when you look at a star, there's a lot to unpack as well. But to me, a galaxy just tells a huge amount of story. Just in like, you can see that you've got in this picture here, the dust lanes. You've got a very bright nucleus here. You have some structure, maybe a gap over here. You know, if I really zoom in here, we get this really high resolution Sombrero image. You can see, you know, the individual stars that are in this galaxy in the dust here, right? And you can see the other backsides of these spiral arms, right? This is what's cool about having a space telescope where you can really resolve a lot of this stuff, is that you can start to look at individual populations of stars here and go, how old are they? When were they born? Right? Like what's the, you know, like, so one of the great pictures in astronomy is HST Andromeda. If we zoom in on the HST, this right here is a Hubble image. That like, if I actually can make life a lot easier, we can really zoom in here. That like, watch as we zoom in on this, right? This is what Hubble can do with our nearest galaxy neighbor, right? So if we just start over here, and I like go back, this is just the side of Andromeda. So if I go over here and we search for Andromeda, and we center, and we really go there. We go that a little quicker. So here's Andromeda, okay? So if I zoom in a little bit, essentially this video is starting like this, okay? So we're just essentially, and if I kind of drop down a little bit, we're just essentially just looking at it from here, because our view on it is, you know, like from the edge. In fact, I think this might be the Milky Way out here. Nope, it's at 32. But like we're zooming in starting here, okay? So imagine that. And now we pop back over here. Whoops, I should turn off this. I keep forgetting I have a window open. We're looking at it from the edge like this, right? And so you're seeing more structure in this. You're seeing all kinds of structure that Space Engine is not simulating. In fact, there's the galaxy that's on the other side. So I guess actually it's more, it doesn't matter. But you're seeing as we zoom in that like all this black is dust and red is like ionized gas that the stars have ionized that I talked about in the past with nebulae. And we're just zooming in and zooming in and zooming in. And notice that all the stuff that looked like static is resolving itself to be stars. Right? We're zooming in, we're zooming in. Every dot in here is a star in Andromeda Galaxy. Oh no, wait, I'm a dummy. I'm a total dummy. This is not what it is. This is the Milky Way. I'm so sorry, everyone. I thought we were zooming in on Andromeda. We hadn't even gotten to Andromeda. This is the Milky Way. And the Milky Way has the Andromeda off to the edge here. So we haven't even gotten to Andromeda. I was like very confused. Like I thought this looked very familiar. Excuse me. See, this is what happens. Sometimes astronomers are totally dumb and wrong. I am totally dumb and wrong all the time. But here's Andromeda. And now with Hubble, this is all. So all the stars you're seeing are in our Milky Way. Excuse me. But as we zoom into Andromeda, things get really fun, right? So all these stars are stars that are between us and the Andromeda Galaxy. But Hubble is such a good telescope that you can start zooming in even more and more on a distant galaxy. And as we zoom in more and more and more, you're seeing what looks like static or noise in the image around here, right? And as you zoom in, you realize it's not static. It's actually stars. So these bright ones are stars in our galaxy. Every other little dot is a star in Andromeda. Right? And so that's the thing, is if you zoom in on Andromeda like we could do here in Space Engine, you'd also see that there's just a gajillion stars, right? Like we're flying through Andromeda stars right now. I'm really slow down here. We're just zooming through all the stars that add up in that image to just look like static in every pixel. And Hubble can take images of that. And what's cool is that you start seeing a galaxy not as some big blob, but as actually a thing filled with stars. Stars that are living and dying and going through their entire life process, right? And so this is what, in the history since Edwin Hubble and many other astronomers started looking at galaxies, the study of galaxy evolution has gone out of its way, has focused on trying to understand all of these processes and how they work together, and why are there different types of galaxies, and what happens to galaxies as they grow, and what makes the galaxy big and what makes the galaxy small, right? And so we can think about galaxy evolution. If I pull up some sort of diagram on galaxy evolution here. It's fun to look at YouTube while I'm streaming on YouTube. We can see a kind of diagram that shows the ways in which we think galaxies actually evolve and grow. And so here's some lecture from the Institute for Astronomy in Hawaii that shows, I don't want to open this in Acrobat, that shows things where we've got galaxies being pulled together initially at long time ago from dense regions of gas and that are dense regions of dark matter, and over time that gas cools and collapses and starts in that gas forming the first stars. Those stars explode as supernovae, and those supernovae, when they explode, provide new metals. The metals allow for other stars to form that are more complicated. They allow for dust to form inside of stars. And so you start getting new, younger stars that also live their lives in these gas clouds inside of dark matter that starts to collapse as well, right? And as it collapses, as I said, any amount of angular momentum as it rotates causes it to collapse and start spinning. So you're seeing here this diagram, this gas collapsing to form this rotating disk with other stars, right? And in that rotating disk, so if we like galaxy formation, I bet we could find some sort of video showing the assemblies of galaxies here. This is a JWST website. Oh man, they're not going to show a video here, are they? Oh, here. Simulation, colliding, evolution of the universe. This is a long JWST video that I don't think is exactly showing. Yeah, so you're seeing here, this is the dark matter simulated that's colliding and collapsing to form larger dark matter clusters, right? And inside of those dark matter clusters, you're getting the gas falling in and all of these tendrils of tiny chunks of the gas that's falling in around. And that's how you get other smaller galaxies like the Magellanic Clouds around our own, right? And so here we can also show, oh man, yeah, two galaxies that are colliding here to form larger galaxies, and you're getting these disks of gas around, right? So you're seeing the disks forming in these simulations, right? And they're pretty neat to watch as a galaxy collects more and more gas and forming these, and in this case, if we go back, you start to see that these spiral galaxies start existing when you get a pristine rotation. But if there's not as much angular momentum, or if you get two galaxies crashing into each other, you actually end up with an elliptical galaxy. And so in the simulation I just showed you here, you're seeing the formation of a large elliptical galaxy that doesn't have that same flat disk structure, but instead is a train wreck where you get, starting here, something that maybe has more of a structure, but as it collects more stuff, the stars kind of spread around and create a much larger blob. So you can see for a little bit, like right here, it starts to actually form, and if I pause it, right here, you're seeing that it's actually right there. It's got a little disk structure, right? It started to make a disk structure, but this is a sped up video. And so for a long period of time, it might be a disk, but then our disk of the galaxy, if I take this and shrink it away, the Milky Way and Andromeda, so if I zoom out, are on a collision course. And so our galaxy, and Andromeda here are going to collide just like you're seeing in this simulation. And when that happens, you're going to end up with what happens in the end of the simulation you're seeing here, which is where this disk crashes into more stuff and that beautiful spiral arm structure just goes away, where you're just seeing a bunch of stars in a big blob. And that big blob we call an elliptical galaxy, especially over time as the stars swallow a lot of the available gas. So the periods of rotation, it's pretty good to know. So how long does it take for our galaxy to rotate? Well, if we go back to our Milky Way, we center on the Milky Way and kind of travel there. Milky Way is way over here. The last time, so the period is dependent on how far around, or how far away it is in terms of how fast it moves, right? But for us out on the edge, the last time we were here, dinosaurs were on the planet. So it's hundreds of millions of years it takes to go around. So the rotation that you're seeing in this video is sped up enormously fast. Enormously fast. You're seeing hundreds of millions of years, if not eventually billions of years going by very quickly, right? And it's probably a little faster as you're seeing it earlier, but like right now our galaxy is probably slowed in its rotation over a long period of time. But it is, for us, hundreds of millions of years, or millions of years to hundreds of millions of years for different types of galaxies, okay? And so the next thing that's important about galaxies, if we shrink this up, as was said in this slide, is that galaxies aren't like stars. Stars exist very far apart from each other, and so it's very random for stars to crash into each other. Galaxies crash into each other all the time. And so you see that when I zoom out, if I like really zoom out, like this group of galaxies all around each other, they're not like stars. I can see how big the Milky Way is. Can you see all the galaxies that are in this group? If I bring up this kind of silly thing here, I said if I bring this universe, it does not want to do the universe map right now. Oh well. If you bring up the local cluster, you can see the galaxies, they're all kind of rotating around. If I like you do this, you can see them all, right? Because they're a little more fixed compared to the background galaxies. But you can see all these are much larger compared to how far away they are than stars are. Stars are pretty big, but compared to how far away they are, they're actually very small. And in this case, galaxies, because they're this big, they crash into each other all the time. And so you get galaxy mergers is what we call it. And so like if I bring this back up right now, you can see typical galaxy merger images in this, for instance, you see the antennae, right? NGC 4038. I wonder if that's simulated in Space Engine. I should know these things before, but NGC 4038. Center. Yeah. So here you see a simulation of galaxy merging, right? So you see two galaxies that they've kind of simulated with these long tails in the process of crashing into each other, right? And you can see that in this kind of silly simulation, they don't have the complexity of the actual version. I guess you can't actually see, right? Because I have, but like in the actual version here, you can see that that they are, right? So if I bring up, let's actually do NGC 4038. We zoom out on NGC 4038, right? So here's the actual antennae galaxies, right? That's what this is called. So this is a zoom in on the antenna, but like if you zoom out on the antennae, it looks, oh man, is it not going to actually show the actual zoom out on the antennae? Why did it have that picture then? Here, you can see that it's two galaxies that are in the process of merging. And these tails, these weird tails on it in the image and in the space engine, they're actually what happens when the two galaxies crash into each other. They send these tails out. So let's look at a galaxy merger simulation, right? I think that there's a galaxy merger simulation. Here. So let's look at a classic galaxy collision simulation right here. So you can see that they've simulated these two galaxies as two disks of stars in the process, like the Milky Way and Andromeda. And now watch as they first interact. No stars are crashing into each other here. This is just gravity yanking stars that are in a pretty pattern around. It speeds up as they get closer, but gravity starts to pull them. And now watch right, boom. Look at this. That perfect spiral structure has ended up with this big long whip tail and this big long whip tail. Does it look familiar? Right? Does it look familiar? Do you see whip tails in galaxies? And so as you watch further, the centers are going to continue to get closer while these big whip tails kind of fling around. And so you're starting to see the formation of a kind of train wreck of stars in the center, like a elliptical galaxy, as the stars in these whipped tails become more dispersed and a little harder to see. The observations of this sort of thing is an entire science, looking at our own Milky Way to see evidence for this happening. Hi, Cheetah Sweater. Nice to see you. Welcome to Astronomy. I haven't done a lot of Mario Maker recently, but it's nice to see you here. So you may wonder, has this happened to the Milky Way? Well, does the Milky Way have tails? If we look at the Sagittarius stream here, let's find images of the Sagittarius stream. These are simulations. This is an actual image from Sloan looking at a huge chunk of the sky where you're seeing light over density from stars in a stream around our galaxy, like a tail, but not exactly. And what it is that our galaxy has been a little bit hungry in the past and has swallowed gas and stars from like entire galaxies as they've gone around, right? So you can see that you've got these videos, these images here that I show, showing our galaxy like eating other galaxies, smaller galaxies. And in that video that I showed earlier, you're seeing, it's hard, but like Milky Way simulation. If we look up a Milky Way simulation, you can really see here from the University of Zurich, you're seeing these simulations. And the simulation doesn't have the highest frame rate because it's an entire mathematical hydrodynamic simulation. And look at how, as these things come in, they create these other little tails, right? I don't care about the words, right? So you can see these other galaxies kind of flinging in and flying in. And it looks really messy, like you're making some sort of delicious egg dish, right? But like all of this, like this looks like egg drop soup or something like that, And all of this is a formation of the gas and stars in our galaxy over time, cannibalizing, I shouldn't use the word cannibalizing, but swallowing smaller galaxies as they come in. And what's amazing is you can use this information to tell about the history and mass and size of our galaxy. So I want to highlight Kritina Besla, her graduate student Ekta Patel, who she works on this, doing this, looking at our galaxy and the orbit of the Magellanic Clouds around our galaxy, right? So here's a really cool a picture showing the Milky Way and the tails and these streams from the Magellanic Clouds as they pass around our galaxy. And this allows us to tell, are these on the first pass through our galaxy or on the second pass? So in that video I showed in the simulation, you could imagine that something's going to fall in a bit, right? If we kind of zoom back, you can see how things fall in, like a galaxy bit might fall in a second. And like that might be its first pass through. But some of these they've passed through and they've gone around a bunch to make these beautiful arms around it. And this is work that she's done that I think is really incredible, along with her, now it's a postdoc, Ekta Patel, and Michael Boy and Kolchin and some other people here. But like this is really cool research. And it's like stuff that you can tell that's like, it's like looking at these tails and looking at these mergers as an archaeological evidence of what's going on. And what's amazing is that when this happens, when the gas falls in, well, if you want to understand how stars are formed, in order to make new stars, you need to take galaxies. You need to take gas and compress it. You need to take that gas in a galaxy and push it together so that it can form the new stars in the centers, right? Like a gas cloud on its own may not have enough pressure to start it collapsing. And this process of making this process here of merging actually triggers gas to start collapsing to make new stars. And so this is something where you can look at these. And so like if we look at the center of, if we look at the antennae galaxies again, and look at that famous Hubble image. So if I bring this back up and say right here, and we look at this Hubble image here, notice that this is a zoom in on one of these two, weird shrimp that have kind of collapsed in on itself with these two galaxies. But what you're seeing here is all of this blue is baby stars being born. And all this gas is gas from star formation. And so this is triggered star formation that from the spiral galaxies that interacted maybe a few 100 million years ago as they crashed into each other. right? This is maybe one of the nearest and youngest famous, so here's a zoom in. If we look on YouTube here, we can zoom in on this, the actual galaxies, right? So this is a summer constellation. You can actually look at Corvis right now in the night sky in the summer if you're in the northern hemisphere, but that's an entirely different video series. So as we zoom in, look, there's the two shrimpies that have kind of collapsed, but we get really close. You see that what you're actually seeing is you're seeing the nucleus of one and the nucleus of the other, right? Isn't that neat? This is one of the shrimp heads and this is the other shrimp head, but this galaxy has two former galaxy nuclei that are going to merge to form one. And you're seeing all this blue stars is baby stars likely triggered. And how do you tell that? How can you tell that it's likely triggered? Well, we can do our archaeology and we can do our aging of these stars and tell how old they are. And that's pretty cool that we can try that into the galaxy formation and the galaxy merger. Right, so galaxy mergers are very powerful, and they probably happen. Galaxies probably go through quite a few mergers, maybe one major merger like this, which is what we call a major merger in their life. But mostly, galaxies go through a lot of minor mergers, like the one it's doing with Magellanic Cloud, like the one I was describing from Dr. Patel's research and Dr. Bez's research, which is pretty cool. Right? So galaxies, to take a step back, galaxies come in different types. They're formed from stars. The stars in them, like some galaxies form a lot of stars, like spiral galaxies and irregular galaxies especially, are forming quite a few stars, right? Elliptical galaxies, while they might go through a period of star formation when they have their initial merger, over time, they aren't forming a lot of stars. So if we looked at like an elliptical galaxy, let's just see, NGC elliptical galaxies, 4486? Sure, let's look at 4486. NGC 4486. We kind of fly over there. So here's an elliptical galaxy. You're probably wondering, it looks like a star. Well, it's actually many, many, many stars. As I zoom in, you're seeing all these stars. So this is what it's like to live inside of an elliptical galaxy here. Right? Bright with stars. Pretty bright. Whoa. I'm going to slow things down quite a bit. You're seeing all these stars. And these stars are older stars. They're stars that lived, were born quite a long time ago, and there's not a lot of new star formation, which is why you're not seeing a lot of blue light here. Just a lot of red and yellow older stars, right? If I click on some random star here, you're seeing this is a yellow dwarf, kind of like our sun. It's got 8 planets if we go there. Maybe we can find an Earth-like planet, I wonder. So here's our yellow dwarf G star. Oh, man. Oh, some of them are really hot. No, it doesn't look like there's anything that's at... One of them's really hot, 909 degrees Fahrenheit. This is 280 degrees Fahrenheit. So nothing is really... But, if we go here... Cool super Neptune. Whoa, it's got 33 moons. So yeah, here's just some planet and, around this. It's likely that, life could be supported in this, but it's, it's tough to think about this because we just only know about life in our one solar system. But that's just one star of the many, many billions in elliptical galaxies. Elliptical galaxies are profoundly, profoundly big. So they're some of the largest galaxies in the whole universe. See, there you go. This is an elliptical galaxy. And it's probably what happened after a long period of time where two spiral galaxies collided, or maybe multiple spiral galaxies collided. This program I'm using is called Space Engine. It's incredibly dope. If you've never played Space Engine, it's like really amazing for galaxy stuff, for universe stuff. It does a pretty cool job of simulating galaxies and allowing you to fly from one galaxy to the other and then fly into the galaxies. So here's another spiral galaxy. Here's a question. What type of spiral galaxy is this, right? NGC this is M91, Messier 91. So if I turn this back on, we can look at what M91 looks like in the actual image. No, that's a gun. There's too many, galaxies that are also guns. So here's the picture of it as it actually is. Can you tell what kind of spiral it is? I see a bar. I see it's not super tightly wound. So it says up here that it's a SBB. Right? So it's not an SBC. It's maybe more tightly wound than our own. And I wonder if that's corroborated by the Wikipedia, which says that it is an SBB. Yes. Which is pretty cool. Right? A barred spiral. Pretty nice. Let's turn off the thing. How can we tell what shape a galaxy truly has from our vantage point? Good question. Elliptical galaxies are insane, but all galaxies are insane. Elliptical galaxies are neat in that we generally call them quiescent, and the question is, why are some galaxies quiescent like that? Why don't they have the gas that this galaxy does? This galaxy here has a bunch of gas, so it's making a bunch of stars. But like, elliptical galaxies don't. What happened to the gas? Did it all go into stars? Did something blow the stars away? And we'll talk about that in a second. So if I center on this, so here's the question that Master Tatsu had. And so Master Tatsu's question is, how do we know what their true shape is? Well, here's the thing. Generally, if it's a galaxy like this, we know that there's probably very little that would actually make something be shaped like a needle with a blob in it. And so we always tend to assume that spiral galaxies are circular, which means that we look at one, we can make a correction. Whoops, let's go up here. We can make a correction. Like if you see it like this, you can make a correction saying, I see it edge on like this, but it's probably more circular. And so you just can essentially, in the same way you might use Photoshop to predict what some shape might be if you were to bend it out and stretch it out, like that's what we have to do. But you're right. If we don't have a three-dimensional vantage point, it's really hard for us to tell what the shape of the Milky Way is. We have to be very clever about looking at gas in our galaxy and at different latitudes, latitudes as we look around the Earth, or right ascensions and declinations, to say, in this direction there's some gas here, and this is not any gas. And like if you look at number counts of stars, you can tell that the galaxy is, not even the fact that it's just a Milky Way in the sky, but you can tell that it's probably very flat. The size of it, we can kind of tell based on how far away we are from it and the number counts of stars, but it's pretty tough, right? Now, the big question is, what's in the center of a galaxy? So if we go and we center this right here, and we go, I'm just going to zoom out, isn't it? I want to zoom in to the center of this. This is actually here. We'll go back to the Milky Way. Whoops. Stop. No. There we go. So let's go back to the Milky Way really quickly. What's in the center of galaxies, right? So we see that in the center of galaxies, it's not as blue, which this red here, this is probably older stars, kind of like an elliptical galaxy, in that this is a population of older stars. And you can see that unlike the disk, the older stars in the center have this bulge. They're like a blob. It's kind of like having like a big a little baby elliptical galaxy in the center of our galaxy, right? And similarly, if we go in the center, to Cheetah Sweater's point, you can see, insane things. Well, look at this. This is a randomly generated nebula that's over here. Wow, very cool, right? Pretty cool nebula. They've simulated it here in this. So here's something where stars are maybe being born in the center, and you can see some baby stars here. But the star formation in the center of the galaxy is not nearly as populous as it is in other parts of the galaxy. And so the question is, what's the very center of the galaxy? Well, let's look. And I'm going to talk about this. So if we center in the center of the galaxy, and we go there, we get a lot of stars. You're getting a bunch of stars. Notice how much more dense it is with stars as you get to the center of the galaxy. More dots flying at us, right? It's really populous with stars in the center. Look at how many stars, right? Really dense with stars. And boom, we get this. So if I zoom out, you can see quite a few stars all in the center. These stars are simulations of real stars. Hopefully you can actually see that. It's not, yeah, good. Simulations of real stars. And if I turn on their orbits, I think I can turn their orbits on over here, right? You can see that the orbits all kind of fly around this. And I think I did this last time, right? Did I do it last time? Did I talk about this? Well, we're doing it again. And so this is what we find at the centers of galaxies, is a bunch of stars. And at the very, very, very center, we find objects like this. So this is a black hole. This is the Sagittarius A star black hole. So this is, I'm going to really change this. Let's turn off the orbits of those stars. Slow down quite a bit. And so here's the black hole and its disk around the black hole. And this disk is glowing because as the gas falls on the black hole, it's getting very bright as it tries to fall and lose some energy to get in the black hole. And it's making a jet of gas and light that's coming out the top, which is why it's really hard to see. And as we go near the edge, you're seeing the bending of light around the black hole, which makes this weird halo, this little hat on top. Yeah, Cheetah, you should buy this game. It's like $30. So it's quite a bit. Maybe there's a Steam sale on it for it, but it's totally worth it. It's like the ultimate type of like zone out, turn on some music and fly around. And it's got like lots and lots of really cool things going on that allow you to you really, see this black hole on both sides, right? Whoops. It's one of my favorite games. It doesn't require a super beefy computer, but like really allows you to see some very cool things, right? So you can like really see this disk of gas falling on the black hole pretty well. So pretty neat. And the thing is now, so let's zoom back out to the Milky Way and turn back on. We think every galaxy has at its core a black hole. Every galaxy. Maybe some of the smaller galaxies have smaller black holes that are very tough for us to find, but there are billions of black holes in our galaxy, and then the Milky Way's black hole is 3 million, 4 million times the mass of one black hole. So it, like one sun-sized black hole. So it's a big, beefy guy, but it's not, or lady, or person, or thing. I shouldn't give it a gender. But the thing is that we now know that most massive galaxies have black holes we can see, and some have black holes we can't see yet, but we think that they're likely there. And this right here is a really important thing, is specifically with the fact that, I wonder what that red thing is way out there. It's just an elliptical galaxy. With the fact that black hole had to grow in some way. And when a black hole grows, it gives off light in the way that you're seeing there, where with Sagittarius A star in the center of our galaxy, whereas the gas fell on it, it got very hot. And so the question is, what happens if you make a light source that's that bright in the center of a galaxy? Does that have an impact on the galaxy? And we'll talk about AGN and quasars in a future installment of this. But for right now, I want to leave you with the tantalizing, we'll talk about AGN in the future. And AGN are very, very cool, right? If we zoom out to larger scales, so remember, every dot here is a black hole. Notice you get, or not black hole, it's a galaxy. Notice you get groups of black hole, I keep saying black hole, I mean galaxies. Groups of galaxies, but you also get these like bands here, right? Which is interesting. Like this band of galaxies is in some ways just, a trick of the way that we're looking at this. But in other ways, it's actually a real band of galaxies. And so if we go back and I turn back on my window here, and we look up large scale structure, you can see that as we did simulation, so this is a survey, this is an image from a survey here that looked at galaxies and their distances. We started seeing that there were these, there were these like pockets. Every dot in these images is a galaxy stretching out not that far to redshift 0.3, which is pretty close by. I wrote Cheetah, I'll answer that question in a second. This is actual data here showing actual galaxies from the 2-degree field galaxy redshift survey, where they took a 2-degree field on the sky and said, all right, how far away are those galaxies? And they found that galaxies have like pockets of no galaxies and then pockets with more galaxies. And we said, well, how do we simulate that? And so these are simulations right here of galaxy voids and filaments, which is what these things are called. And these are commonly shown to look like neurons in our brain. But these are essentially simulations showing how this might happen. So if we look up the Millennium simulation here, which is a famous simulation that, you can see. I want a HD Millennium simulation. I want a really good one. Yeah. That's not as good. But so Cheetah asked, I assume a lot of these simulations are like guesses what these galaxies will do. We have like that level of info. So this is a simulation of galaxies, but it's a simulation mostly of what we call dark matter, of the material that kind of holds galaxies together and holds the universe together. And this simulation shows that over time, in a similar way to the way galaxies form, dark matter flows into these filaments between these big pockets, these halos of galaxies. But this is just entirely a simulation. The research that I've been showing with Space Engine, and the stuff I've been showing with Space Engine is kind of a guess in some cases. Like some of these are guesses. Did I just click on the Milky Way randomly? That's incredible. How did I just do that? Like here, if I look at 4220, this is entirely a guess based on some images of what NGC 4220 looks like. So if I look at this, and then we bring up, I guess you can't actually see this because the simulation is in the way. This is it. Let's look up the NGC 4220. NGC 4220. This is what NGC 4220 actually looks like with actual astronomy images, right? And so you're seeing here, you know, not bad. If I shrink this down a little bit, let's bring this up. If I shrink this down a bit, you can see that, like, I could probably space engine it up so that we are looking at it in a very similar way. Is that similar enough? Yeah, I can rotate it a little bit more. But space engine is kind of guessing. And also, any amount of, here we go. Any amount of like stars that are in here, we don't know anything about the stars in NGC. Maybe a couple in these galaxies. This is 4631? Yeah, 4631. Did I click on the wrong one here? I think I'm looking at 4631. There we go. I'm a dummy. What? NGC 4631 is an irregular galaxy. So it's not even a great... Oh, it's a barred spiral. It's a barred spiral that kind of looks like a irregular, right? Here's an HST image of the same galaxy, right? So we're not, you know, it's not exact, right? Like it's close, but it's, you know, it's not doing a super great job, right? So like, it turns out that Space Engine's simulating these things, and then also inside, Space Engine is, you know, if I click on some random star here, we like kind of fly into the galaxy, and we click on a random star. This is a random star. You see it says RS, and that's a randomly generated star. So everything here is entirely simulated, right? But you see that there's quite a bit of stars. In the very center here, stars and nebula, like this is just a random generated nebula simulated within this program. I wish we had the capacity to see this, but we don't. We, you know, right now Hubble, the best that it can do is what you're seeing here, which is this is the best Hubble can do and the best we can do right now with understanding what's going on inside of this galaxy, right? And we can see pockets of gas, but we can't see nebulae like this. So this is randomly generated, right? Which is pretty cool. So it's just about an hour, and so if there's any other questions, I want to kind of finish here. I think I've explained, like, you know, galaxies and a little bit about large-scale structure. I'll probably go into a little bit more detail about some cool aspects of galaxies. I like talking about mergers and stuff. But if you have any other questions, you should let me know. I'm going to put on my classic Twitter and Instagram. You should follow me on both of these things. After this, I'm going to try something interesting. I'm going to see if I can stream on Instagram with some of this to test out, because I think it's possible for me to do this streaming on Instagram. Which would be kind of cool to like show off this program on Instagram. But I once I get off of the YouTube, I'm going to do that. Because ideally, it'd be cool to like stream on both simultaneously. Although then I'd have to move my window. I'd have to move myself over here, or else I would be off the edge of the screen on Instagram. But it's nice to see you, Cheetah. And thank you, Master Tatsu, for showing up. And again, I'll see you in a couple weeks. And then also in a couple weeks, I'll do another one of the July... How to Stargaze. And Cheetah, if you've not watched that video, it's pretty cool. I think there's a lot of really cool. How much will JWST augment these images? Well, James Webb will have a higher resolution, and it'll have more sensitivity, and it'll peer through a lot of the dust. So if we want to look at like something like here, I'll do one more thing before I finish up window capture. If we look up Spitzer versus Hubble, let's look up. Yeah, here we go. So this is an image in the visible versus in the infrared of the same gas cloud. And you might be looking at the infrared one and going, oh, that's not nearly as pretty. But the thing is that you're seeing all of the stars you can't see in the left image. The left image is just showing what you can see in the visible, and a bunch of dust and gas is blocking our way of seeing this. So James Webb will offer us a higher resolution image in a wavelength range that allows us to peer through dust and gas, which means for a galaxy, so let's look at Andromeda. Optical versus infrared. This is a classic example. Here's a picture of Andromeda in a series of different... So, optical's in the top left. This is a galaxy we looked at, Andromeda, right? But then, if we look over in the middle, we see infrared, and on the right is the infrared as well. Notice that you see a whole bunch of rings of stars that, like, you know, you could not see in the generally the optical image, right? The composite in the bottom left shows where they are, and you can see that they kind of correspond to dust rings in the top left because dust is blocking the way. The infrared is very cool, right? And that's what James Webb will offer. It'll offer us a wavelength of light we cannot do right now with Hubble, and a resolution and a sensitivity that is unmatched, unparalleled, right? Pretty cool. Cheetah, I recognize, I lived in LA for many years. If you can do stargazing in LA, you can do stargazing anywhere. And like, you should learn, it's not hard. It's totally worthwhile. And I know you can see some stars. Unless it's raining like it is right now, you can see stars. You just got to, you know, make your way out of town a little bit or make your way someplace. And it starts with just the brightest stars. Trust me. Okay, well, I'm going to finish there. It was wonderful to see you all. Have a nice, whoops, that's me going away. It's wonderful to see you all. Have a nice rest of your afternoon or evening. And I'll talk with you guys in the future. Bye, everybody. I'm going to make sure that I don't stop streaming until I actually have finished, because I did that last time and I cut off the end of my video. And so now you're just going to have me rambling at the end of the video, in which case, you know, that's how life goes sometimes. If you want, you can start joining me on Instagram right now, because I'm about to just like try to stream on Instagram and see how that works. But anyway, bye, everybody.